I'm, along with Kenneth Shankland here, the co-director of this school. And welcome, all you who are wearing, well, I'm wearing an orange one actually, so I'm clearly in the wrong place. But welcome here, all of you who are on the powder diffraction course. As I said at the beginning, I think what Kenneth and I want to be able to do is to have a chance to learn, but to enjoy and to learn at the same time. This is a fantastic place. It's a fantastic opportunity for you students. We have many of the world leaders in the respective fields in powder diffraction here. It's an opportunity for you to meet and discuss. And for you speakers, actually, I know half of you, it's a chance for you to relax as well, actually. So hopefully we're all going to enjoy ourselves. But it's a pleasure to introduce Kenneth Shankland from the University of Reading. Again, I say he's the co-director with me on this course. And he's going to start things up, actually. We're going to start at the basics and talk about data collection. So over to you, Kenneth.
Okay. Thank you very much, Bill, for the kind introduction. Let me add my thanks to the local organisers in Pawley in particular for all the hard work that they've done in pulling the programme together and making sure that you safely. I've got the unenviable task, I believe, of kicking off 10 days of concentrated powder diffraction. And so I decided that I would take our inspiration from Julie Andrews in The Sound of Music, that we would start at the very beginning. It's a very good place to start. And that leads us automatically to data collection. Now, as we'll see from the next talk from Peter Stevens, which is on Rietveld refinement, Peter harks back to a meeting in 1995 that was held in Oxford entitled Structure Determination from Powder Diffraction Data, that Bill and I and Devinder Sivia were involved in organising. And I remember very, very clearly then being starstruck at the number of speakers and the attendees that we got. And the feeling here is very, very similar. It's just fantastic to see such a gathering. Now, those of you that know me and that have heard me speak before will notice that I'm speaking probably quite a bit slower than I normally do. I'm from near Glasgow. Originally, I spent really the last 20 years in the deep south of England, 15 years at the ISIS facility in Oxfordshire, and then the last couple of years at the University of Reading in the School of Pharmacy. But I think it's probably fair to say that my accent hasn't changed a tremendous amount. That's doubtless helped by the close collaborations with Bill. But anyway, I'm going to speak slowly, so hopefully you won't have too much trouble following me. In terms of background to data collection, it's an enormous field, and I can't possibly hope to cover it. And I will say from the outset that I don't even intend to do a review or a comprehensive study of different data collection techniques. So what you will get from me is a very personal view of data collection. I've been collecting powder diffraction data really in one form or another since 1990, starting off on a Siemens, now a Bruker, D5000, and then at the synchrotron facility at Daresbury on stations 9.1 and 2.3, then making the transition to the ESRF, to the bending magnet, and then to the insertion devices, and most recently, in-house on Bruker D8 Advances and at the Diamond facility on I11. And in all that time, working mainly with molecular organic materials, we've encountered a number of different problems. And what I'm going to try and do is use some of those problems to illustrate the way that perhaps we should all be thinking, and perhaps those of you that are embarking on careers that involve powder diffraction or have cause to carry out powder diffraction experiments, maybe some hints about the way that you should approach your experiments. And hint number one is that you could do an awful lot worse than get yourself a copy of this book, of which I was one of the editors, and read this particular chapter here by Rod Hill and Ian Madsen. Ian's in the audience today, And they wrote a very, very clear and concise chapter on the things that you should be thinking about in setting out to collect powder diffraction data. It's an excellent read, a model of clarity, and I would strongly recommend it. And many of the elements that are in my talk today, you will see, have been largely lifted from the guidelines that they have provided. Now, in the spirit of the sort of discursive nature of the meeting here, I thought I would begin with something rather philosophical about data provenance. So I'll leave you to read this statement from someone at the University of Pennsylvania, really talking about provenance of data as it is distributed worldwide via the World Wide Web. And he is arguing that the provenance of the data, i.e. where it came from and how it was originated, is actually a significant factor. We're all guilty of going to Wikipedia and looking for images and picking them out. And sometimes we don't stop to question where they came from. Have they been tampered with in any way, modified? And I would argue that this data provenance is true of the vast majority of scientific data. When I was at ICIS, I actually spent quite a bit of time working on computer science projects to catalogue the data that we collect at the facility. And they are issues of how the data was tagged, times, dates, collectors, instruments, microamp hours, all became very, very important. But I first became aware of data provenance issues back in the early 1990s when I worked with Chris Gilmore in the Department of Chemistry. And those of you that know Chris will know that in the early 90s he was working very, very heavily on the technique of maximum entropy applied in the field of crystallography. And it was seen then as a very advanced technique. It required a lot of computing power. And it was almost seen as a magical technique because it could reconstruct information that wasn't already in a problem. And many people would approach Chris with data sets and say to him, can you try maximum entropy on this data set? We haven't been able to solve it. I would like you to try. And Chris, being a very helpful guy, would always say, yes, certainly we'll give it a try. But the data that we received was usually a list of structure factors, HKLs, F squareds, and sigma F squareds. And we began to work on that, and sometimes we're successful. Other times we would fail miserably. And in many occasions where we failed miserably, we made further inquiries, and it turned out that something horrendous had happened during the experiment. And it wasn't simply that it was a difficult structure, it was simply that it was a bad experiment. And nothing was going to salvage it, not even the magic of maximum entropy. So when collecting data, I think it's very important to make a note of how it's collected, of things that go well and of things that go wrong. Because if someone else is going to work on it, they have to know. Now here's an extreme illustration of, does it really matter noting how you collected your data? Well, yes it does. Here's some data collected in a lab instrument in transmission capillary mode. Really, really nice sharp pattern. Here's the equivalent data set collected off of a flat plate. It looks completely different because the intensities have been completely distorted by the effect of preferred orientation. Simply the limited sampling that we have on a zero background plate with crystallites oriented in very particular directions, leading to excessive intensities on some peaks and very, very poor intensities on other ones. Now, if you were given that to work on without knowing a priori that it was flat plate, and you assume that all intensities are on an equal basis, then you will probably fail miserably. If, on the other hand, you're given this, you could probably be quite successful in solving and refining the structure. Now, that's not to say that you couldn't do the same thing on this, but you would need to know in advance the fact that it had been collected in this particular way so that you could factor in into the account the possibility of preferred orientation. The other thing I would encourage you to do is, what do you want out of your powder diffraction experiment? Or more to the point, what do you think you want? And there's a very subtle difference. And this is an example of a pattern that we were sent fairly recently from a person who was conducting a co-crystallization by grinding experiment. He took two crystalline materials and ground them, and he expected that they would go to an amorphous phase, and then subsequently, over a period of about 3 weeks, that they would recrystallize and give a co-crystal, which in fact they did. But at the end of the 3-week period, when we solved the structure for them, we found that present in the sample, the blue tick marks correspond to the co-crystal, the black and the green tick marks actually correspond to starting materials. So we can index, okay, once we're aware of that, we can index, we can extract, we can solve, we can refine, all straightforward. But the obvious question is, was that starting material there at the end of the grinding experiment, or did in fact it recrystallize in parallel with the formation of the co-crystal? So we emailed to say, did he have any data from the end of the grinding experiment immediately once he'd finished the grinding? And this is what he sent us. And it would be a brave man who said that he could spot any, brave man or woman, who could say that they could spot any crystalline peaks in there. There's maybe a hint of something slightly sharper and maybe just a touch above the noise level there. But the point was that when we asked how long he'd collected the data for, it was about 30 seconds. It was a hyper-quick scan because he did not expect it to be anything other than an amorphous mixture. And so his data collection strategy reinforced that. So we can't actually tell anything really worthwhile out of this. And if he had anticipated and thought about the possibility of contaminant, shall we call them, starting material peaks, then he could have quite easily adjusted the experiment, counted for longer, and any residual crystalline material could have been picked up. So it's not so much what you want out of your experiments, what you think you want, or what you think you might want down the line. And Ian in his chapter mentions a number of possible outcomes of a powder diffraction experiment, of which just a few are listed here. The typical one of sticking the sample on to see if it's the crystalline phase that you expect. A quantitative phase analysis, indexing, solving, and refining. And each one of these different experiments has its own requirements in terms of peak accuracy and peak intensity accuracy. And you can tailor your data collection strategy according to the outcome that you're looking for. Some of the things to consider when you're setting up your experiment are the choice of radiation, the geometry of the instrument that you're using or that it can be set up in, the way in which you prepare your sample, and the way in which you actually collect your data. So in terms of the choice of radiation, I think most of us will be familiar with copper, either in its unmonochromated or its monochromated form here, in sealed tube form. But we're certainly not limited to that. There are a number of commercially available solutions from the longer, softer wavelength of cobalt at 1.8 through to the more common and starting to be seen more on powder diffractometers, molybdenum radiation on the same footing as single crystal, and for even harder radiation and possible PDF work to get you out to very high spatial resolution, 0.56 angstrom silver radiation. I'm not going to say very much at all about synchrotrons because we have people speaking specifically on that topic in the not too distant future, other than to say pick a wavelength within the available band that comes off the bending magnet or the insertion device. Why would you want to vary the wavelength or pick a wavelength? Well, you may want to, in the case of the synchrotron, pick the point of maximum flux to make your experiment as short as possible. You may have reason to compress or expand your pattern. If you collect at longer wavelength, obviously everything is spread out. Although the benefits of compression and expansion depend very much upon the limiting resolution, if, for example, you take a pattern and compress it down, you really need to maintain instrumental resolution high otherwise you will start to suffer from peak overlap. And of course, by tuning radiation, you can avoid absorption and/or fluorescence issues. The other thing I would just say briefly about synchrotrons, and in particular the third generation with the insertion device, is that sometimes actually less is more. We find particularly with organic materials, the destructive power of the incoming beam can be quite severe, and this is one of the first ones that we saw a really, really severe effect on. It's actually an antifungal drug called ornidazole, and what we have here is a 1 millimeter capillary exposed for 2 minutes on ID31 at the ESRF, Andy Fitchie's beamline. And each of the curves here shows you a 2-minute data collection stepping from this first one here to the next one. So we collect data for 2 minutes and then collect another 2 minutes and another 2 minutes. And you can see some drastic changes in the pattern as a result of radiation damage over a relatively short period of time. Now, if you don't take account of this in advance and you simply put on the sample, open the shutter and disappear for a cup of coffee and come back, then you're going to find that rather than nice sharp diffraction peaks, you'll have some very, very broad splurges, for want of a better word, in your diffraction pattern. You can actually see the sample radiation damage from each exposure on that capillary there very clearly, these little brown spots here. There will be people in the audience who know an awful lot more about radiation damage than I do. I'm not particularly concerned about the mechanisms of it. We'll see, in fact, probably from one of the later talks, where in fact you can use it to your advantage in structure determination, believe it or believe it not. It takes two forms: primary damage as the X-ray photon hits the structure and causes some damage, and then secondary damage caused by the formation of radicals within the crystal structure and their diffusion and the damage that they cause. Sometimes the damage can be incredibly overt, as we saw in the previous slide, or it can be rather subtle. Certain materials are more radiation hard than others, and it may be that if there's simply a subtle change in the lattice parameters throughout a data collection, then that will lead to an unnecessary peak broadening and really degrade the resolution of the data that you collect. And so to one of the many pre-experiments that's listed in Ian's chapter, I would now add that if you visit a synchrotron, then it is well worth adding a radiation damage pre-scan to your list of experiments. And here's a result of one done very recently at Diamond, a 2-minute data collection on a molecular organic in blue, followed by another 2-minute data collection. This was actually using the crystal analyzer detectors. We then quickly superimpose them one on top of another. There's no significant difference. So this sample is at least good enough to collect data for 4 minutes. In our recent trip to Diamond, the majority of samples that we looked at exhibited radiation damage in a period of less than 20 minutes. So you really have to think about the way that you set up your experiment. Gone are the days, I think, at least without some of the automation benefits that we'll see, gone are the days of, as I said earlier, sticking the sample on and disappearing either to the coffee room or to the pub and coming back 8 hours later for your data set. A potential solution to this is to drop the temperature, do your collection at low temperatures to minimize that damage, and use sample translation to expose fresh sample. So if we go back to that previous pattern, we've worked out that we can collect for roughly 4 minutes at least before there's any possibility of damage. So why not collect for 4 minutes of this point in the capillary, because the beam width is only a couple of mil and our capillary is much longer than that, and then use sample translation to automatically move and expose a fresh piece of sample and then collect another 4 minutes of data. And we can do that right along the capillary, as you would see from this here. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 exposures out of one capillary. which may still only equate to about 20 or so minutes of data, which may not be enough to do what you really want to do. So we can then take advantage of the fact that a lot of diffractometers at facilities are actually equipped with sample changing robots. And what you see here is a photo of the inside of the Hutch and ID31 with a turntable here with a whole load of samples pre-mounted. So we've taken, I think in this case it was a particularly long and complex experiment. We took something in the region of 30 capillaries and pre-mounted them here, and then asked the sample robot to pop the sample onto the goniometer, do the data collection, do the sample translation for each one of the capillaries, and when we'd exhausted the sample on one capillary, pull it off and put the next one on. And then the software can integrate that data for us and give us one very long data set with no risk of radiation damage. Obviously, this is sample hungry, but this was a particularly extreme example. Neutrons, again, we'll hear a lot more about these throughout the week, so I'm not going to say anything very much, other than to point out that they have various benefits, particularly the lack of a form factor, the fact that they have scattering lengths that vary in a sort of non-periodic fashion as against those of X-rays where they vary periodically with the number of electrons. They have excellent penetration properties, so if you want to prepare samples at extreme conditions, I think it's still fair to say it's very much the radiation of choice. You can get a tremendous amount of sample environment around your sample, but still get the neutron probe in and back out and detect it. On the downside, because they can pass through just about anything and they only interact with nuclei, any scattering that you do pick up off your sample is fairly weak. And of course, if you have hydrogen there, you have to worry about the incoherent contribution. But as we'll hear from Laurent later in the week, the advances in instrumentation are making big changes and knocking some of the assumptions about what we can and can't do with neutrons on the head. In terms of the sample geometry, the choices are pretty straightforward, at least within the laboratory. Here's a very simple geometry here with an X-ray source with a focal point that diverges onto a sample held in a flat plate here and back convergent onto the X-ray detector, giving a very high flux, high resolution setup. If we look at the sample in here, we have to worry about preferred orientation in general, crystallite stacking as we layer them in to this sample holder, which is generally made out of something like plastic. And we have a second problem as well with thick samples and organic materials. This is an example shamelessly rehashed from Jeremy Cockcroft's website. Just a simple illustration of the fact that the incoming X-rays that reflect off the surface of a relatively X-ray transparent material will give rise to this pattern in red, but if the X-ray penetrates substantially into the body of the sample and diffracts off, and we collect it, it actually gives rise to the pattern on the left. And this is called the sample transparency effect. It actually results in the peaks moving substantially to the left and also broadening out as well. And if we're in a situation where line positions are critical for indexing, then this is a problem that we could really do without. And so the default way of simply filling the powder into this ordinary background holder is not really a good one. And so it becomes advantageous to use something such as a zero background plate. And these are nothing more than sample holders that are cut from materials such as silicon, and they're cut in such a way that the plane of the holder doesn't contribute any reflections in the area of interest. Tiny bit of grease on the surface of the plate and then a light dusting of the sample on the surface will give you very, very sharp reflections. It requires very little sample, which is generally non-recoverable. It's still, of course, prone to preferred orientation effects. We don't have many crystallites present either, but it's an excellent way of getting very sharp data for indexing and strongly recommended. Another presentation geometry that we can have still in keeping with the, if you like, the bulk sample presented in a flat way is actually to move into transmission. and here have our X-ray source convergent on our detector and going through a thin sample that's sandwiched in between Kapton or Mylar film. Experimentally very straightforward, but we did a few checks in our own in-house setup recently when we were checking out some possibilities for this geometry. And we noticed some pretty severe background problems and got to the bottom of them fairly quickly, and I think they're worth showing here. There's this general upward curve, a rising background from air scatter, which you can minimize by careful adjustment of the knife edge collimator. Because we're using Kapton film, we get this little characteristic bump here. We can get shot of that by just moving over to using Mylar film. The thing that surprised us the most, really, was this very large hump here, which is actually from the plastic sample holder that actually holds the Kapton film in place. And that's a function of the fact that the hole in the sample holder for actually holding the sample is about 7 or 8 millimeters wide. The beam itself that impinges on the sample and the holder is in the region of a couple of centimeters wide. So we're actually scattering very, very strongly off the plastic ring. We can get round that just by simply narrowing the beam at the monochromator exit slit, and then this part will disappear completely. And that's important because if we're looking for weak reflections, particularly in indexing, we don't want to be fighting effects such as this that will help mask the coherent diffraction. Bragg scattering, I should say. And my own favourite geometry within the laboratory is that of the convergent beam onto the X-ray detector, but this time with a sample held in a capillary. And I think it's pretty widely recognised that if you want samples that are largely free, or as free of preferred orientation as you can, then this is the best way to do it. The capillaries themselves come in all shapes and sizes. In the geometry that we saw on the previous page, the narrower the capillary that you can use, the sharper the diffraction is likely to be, assuming that the diffraction is not sample limited. Filling a 0.3 millimeter capillary can be rather tricky. So in practice, a 0.7 is probably a good balance between getting a decent volume of sample into the beam to scatter strongly and also making it relatively easy to fill. There's all sorts of tips and tricks out there for how to fill capillaries, ranging from scooping up the powder in the top and then tapping it with your finger to rubbing a file on it. Our own personal favourite is one that Dave Cox showed me at the NSLS many years ago, and that is putting the capillary inside an empty shell of a cheap biro pen and then tapping it on the desk. Cheap, easy. And the most recent variant that I saw at Diamond was someone with an electric toothbrush encouraging some stuck powder to go down by vibrating it. Cheap, pretty effective. But the simplest advice is don't be greedy, just put a little bit of powder in at each time and tap it down. If you're greedy and you try to overfill, it's going to stick regardless of what toothbrush you happen to have. Now, I don't know if many of you will be familiar with this, but this is an instrument that I saw a demonstration of fairly recently that actually allows you to do powder diffraction on the move. Now, I should say in advance, I have nothing to do with the company. I have no interest in promoting their product. I simply want to illustrate a point, and it's easy to do that in context. This is a portable XRD intended for use in the field. It can be run off of batteries. It contains a microfocus source, an area detector in the form of a rectangle, and most interestingly, from this talk's point of view, a rather unusual sample holder that we can zoom into. And in fact, it includes a piezoelectric actuator, not a million miles from what is inside the toothbrush, to actually induce powder flow in the sample held in a cell with some X-ray transparent windows in it. So there's the sample holder. You pop the sample in, put the window back on, put the sample into the machine, and when you switch it on to data collection mode, piezoelectric actuator kicks off, and you can actually see the powder grains moving. It was really developed for technology that was sent to Mars on Explorer missions, where you crush rocks and feed the powder down through and analyse it. And it's incredibly effective and certainly well worth a look. Okay, to grind or not to grind, that is the question. If you're given a sample and it looks rather sticky or the crystallites look a little bit large, then there's a strong temptation or clear benefits to reducing the particle size. The benefits are that the smaller your particles are, the more representative sample you'll have in your beam, you'll get proper powder averaging. The risk, the main risk that you run is that of inducing a phase transformation due to pressure or temperature effects. Of course, you're likely to induce some line broadening, but that may not be that important if the resolution of your instrument is limited anyway. General rule, if the sample appears to sparkle under the microscope, the crystallites are too big. If they're sparkling a lot, then you should be getting in and trying to pick a crystal out and speak to your friends with single crystal diffractometers. But even those that are too small for conventional single crystal can still be too big for powder diffraction. Let's just remind ourselves of what a powder diffraction pattern looks like. It does. We have here a single crystal. We have lots and lots of tiny single crystals. And so when we average them round, you'll see them tracing out circles. And so if we collect with an area detector, we'll see a diffraction pattern like that. But typically, we're cutting through that with a detector, and every time we cross a line, we record the familiar powder diffraction peak. And if we have a sample where there's some non-uniform distribution inside, then this is the sort of thing that we see. Some lines are, some reflections are uniform, other ones are not, representing an uneven distribution of crystallites. And in extreme cases, these can be lead to some pretty severe abstract artifacts. So we're looking at a sample that was sent to us recently, and this was the data set that had been, the quick data set that had been collected with it, and the chap was claiming that he had a new phase of a material. And he knew that because he had a double peak at low angle, and he had never seen that before. So Mark, the PhD student at Reading, collected the data. We saw exactly the same thing, but then he reported that it looked rather sparkly, the material, and should he grind it? I said, yeah, give it a grind and recollect. And mysteriously, this peak completely disappeared, and we're back to single peak. And the answer to that is, in fact, there was only ever one peak there to begin with, which has a shape such as that, and this apparent peak here was nothing more than a very strongly scattering crystallite leading to a blip on the diffraction ring. So simply by not grinding, you could be misled into thinking that you have, for example, two long axes here, when in fact you only have one single peak. We've done a few unusual sample preparations. The first two are actually basically the same thing, freezing a liquid or quench cooling something that you originally melted and then froze within a capillary, or inducing crystallization in a saturated solution by freezing it. In each case there, the distribution of crystallites within your sample is likely to be non-random, and you can end up with some very, very severe preferred orientation effects. If you're aware of these in advance, then sometimes you can do something about them, but it's certainly very unusual to get a material prepared in this way that is not free of effects. And we'll see an example in one of my later talks of how this can affect data. Okay, count times, I'm not going to labor on particularly hard, because this is something that's been known. I mean, Bill showed really earlier on in his talk that really there's very few things new under the sun. Pretty much a lot of the stuff in powder diffraction was done and dusted many years ago, and count time schemes are one of these things. It's been known for a long, long time. Why do we spend as much time counting at low angle as we do at high angle when we know that there's not so much intensity out here because of the LP effect, and also because in the case of organic materials, the form factor fall off? And of course the answer is that it's the easiest way to do it. It doesn't require any thought, and also until relatively recently, diffractometer control software wasn't really geared up for it. Although interesting, I was thinking back to when, in the early days with Bill at Daresbury, the 9.1 diffractometer could, in fact, you could give it a file with a 2 theta angle and a count time and a list, and it would go off and follow that, which was rather nice. But calculating a count time scheme is actually very straightforward. This is one which gives approximately equal e-values across a diffraction pattern. And you can see that all you need to do to calculate the time to dwell, i.e. count at any particular value of theta, is a function of equation that has some average scattering factor, say in the case of an organic we'd use nitrogen, some average B factor to quantify what temperature we're sitting at, and some other unknown term of angle and wavelength. Very, very straightforward. That gives you a continuous distribution shown in blue here, but it's actually much easier just to say, well, we'll do a block approximation to that. We'll count over this region for this time, this region for this time, and so on. And the resultant benefits of that are really pretty substantial. So here's a lab data set shown collected for 3 seconds a step for about the first 15 degrees, 10 seconds for the next, 10, 20, 35 degrees, and then 22 seconds a step for the high resolution stuff, where we expect it a priori to be weak. At the end of the data collection, everything is normalized back to give you the final powder diffraction pattern, which will look not that much different from if you had done an equal count time scheme, but of course you have the benefit of knowing by doing this, the accuracy of your measurements is much higher at high angle. And I would strongly advise you, if you don't do this, to go off and look at it. But probably one area where count time scheme is relatively unimportant is when you use a detector such as the Mythen or the Mythen 2. And this is a snapshot that I've taken off the web of one of the SLS beamlines. And this detector actually subtends an angle of 90 degrees. And so it doesn't really make much sense to do variable counting with this, because it's going to count over the full range of general interest anyway. You can still use variable count time schemes with multiple analyzer crystal detectors and do that quite effectively. There are plenty of tricks that you can play with advanced data collection, doing your data collection as a function of some parameter. So let me show you an example here, and it's one in which you vary the temperature of your experiment and watch how a cell, which of orthorhombic or lower symmetry, expands or contracts as a result of that temperature change. Because the cell dimensions change, then the peak positions change, and that can help unearth information that you would miss just in a standard data collection. So here's an extreme example here of the antibiotic chloramphenicol palmitate, just concentrating on this peak X here, 2 contributing reflections, IA and IB, equal to the total area under the curve. Generally speaking, you look at that, we have no basis to do anything other than equipartition the intensities, which is far from ideal for direct methods. If we change the temperature, then we see these peaks actually crossing over and becoming completely separated. IB is now well-determined and strong, IA is well-determined and weak, and that's a much stronger piece of information for feeding into structure solution. And within, Bill was mentioned topaz earlier on, this is actually a 5-temperature polyfit, 5 different data sets at different temperatures on the same material, fitted with one single set of intensities within topaz. The net benefit of this is that you get a set of structure factors where there is a quantifiable benefit. Rather than simply saying we couldn't solve the structure and then we did the DTE and we did solve the structure, you can look at statistics that show that the R factor comparing your extracted intensities with the single crystal intensities are much better for the multi-temperature experiment than they are for any given single temperature experiment. Amazingly, I appear to be right on time, which is a surprise. So clearly my slow speaking worked out. Summarize then be clear what you're setting out to do with your data collection, and be prepared to change your approach as the data comes off of the diffractometer. Don't say, well, it looks as if it's going to be okay, when in fact it may not be okay, particularly in the case of radiation damage. In all of the excitement of an experiment, don't forget to record exactly how you collected your data. I'm very guilty of it, particularly at the synchrotron where time pressure is on, and you think, I'll remember what I did, I'll put the next sample on. Inevitably, you forget what you did. So make a note of things. And if you do have the misfortune to work on other people's data, make sure there's sufficient information made available to you to make it worth your while, because you could quite happily spend weeks or months on other people's data only to find out that it was doomed to failure from the very start. That's all that I wanted to say, other than to thank you for your attention.
Thank you, Kenneth, for an excellent tutorial introduction to the successes and the pitfalls associated with data collection. We have just under 10 minutes for questions, and I just want to remind you of what Pawley said earlier on, that we are encouraging the younger members of the audience to ask the questions. For all of you who are old like me, actually, I think we have to stay quiet until the questions stop. Hopefully the questions won't stop. And Pawley also did say that there is an incentive to ask questions, and it's not going to be the number of questions that get rewarded. It's going to be what am I trying to say? The depth and the incisive qualities of the questions. Because this is a member of Ludovico Riva. I mean, I guess a lot of you don't know or never met Ludovico. He really is the spirit of Arici. We'll be hearing much more about him later on today. But he was an energetic and a very fine man, and really appreciated very much the participation of the young people. He did this for all these years, really to try to get the whole field of crystallography there, in new and next generations. And so this prize is for the best questions that are asked. And so I'd like to open the floor now, and I expect to see about 50 hands going up to ask Kenneth questions about data collection. Now, what I should also say as well is I need to take your name. So when you
and your age.
yeah, and your age. No. So if you could actually, when you say your question, if you could actually speak loudly so that the folk at the back can hear, but also tell me what your name is. Speak into the microphones. Yes. Yes.
You got to. No. Doesn't sound like.
Okay. Yeah. Okay. Yeah. My question is because my name is Habibur.
And where are you? Could you say where you're from as well, please?
Gothenburg, Sweden.
Okay.
Simple question, not worth of money, I guess. What kind of software you use to do the programming when you say that variable count times? Because I haven't seen this before in our Bruker D8. Does?
The D8 will in fact support collection of variable count times within XRD Commander. I'm not sure on, does it calculate them for you, or does it simply allow you to put them in? The Bruker XRD Commander software, I know that it allows you to input a variable count time scheme. Will it also calculate one? It will do.
Okay.
So I can't honestly speak for other diffractometer manufacturers such as Panalytical, although if anyone in the audience knows and uses Panalytical and says that they can do variable count time, then please, don't be shy, please tell us. But I think for several years now, XRD Commander that controls the Brooker D8 will accommodate these variable count time schemes very straightforwardly. And it's simply a case of specifying a range, a time for each range, and then at the end of it, the data are normalized into a single raw file.
I say, can I do a little? And I say, Pam, put this. Could you put the microphone on, please?
You can actually save a little bit of time by. There's no reason why you can't increase the step size with angle as well to actually save yourself a little bit of time when you actually come to do that.
That's certainly correct, Jess. What Pam's basically saying is that you may not need to spend quite as much or have quite as much detail at certain areas of the pattern, and so you can step through them faster. So basically whiz through the pattern quickly and then slow down and move to finer detail where you want to resolve some peaks.
Can I make I just also want to make a point as well, actually. Kenneth put up the equation. It's a simple equation. Just use an Excel spreadsheet. I think to look for the answer in a piece of software or on from the manufacturer, it's a very simple equation to do. Just pop it into a spreadsheet and you'll be able to do it. Saul.
Saul Lapidus from Stony Brook University. In terms of using multiple capillaries, my experience with these glass capillaries is there's some variation in the width of those. Yes. Using multiple capillaries, you can have different amount of sample in your beam for a different amount of peaks. How do you go about correcting your effective intensities will then vary in the different capillaries? How do you take that into account?
Averaging. So
you run over the different capillaries over the same range?
Yes. Yeah. We simply average out over all of the capillaries that we use. So we're not correcting for that small variation.
Okay. In terms of another question, well, I have you right here. In terms of sample radiation damage, yes. Do you have any experience, variation with different wavelengths?
We've sort of dipped our toe in the water in terms of trying to adjust wavelength and apply filters, for example, and also look at it maybe as a function of, is it anything to do with the intrinsics of the molecular structure? Are hydrogen-bonded materials more prone than non-hydrogen bonded materials? We have not come up with a clear pattern. What was most interesting, in fact, was that when we went back and reanalyzed some very old BM16 data from the SRF, so just on the bending magnet, we actually went back and found that the radiation damage was still there. We simply hadn't noticed it. It was much more subtle because of the lack of flux, or relative lack of flux on the bending magnet. The minute the machine was upgraded to the insertion devices, then it became instant that this damage was occurring. So it's primarily, so we have not done anything exhaustive or looked into it in any sort of theoretical fashion, but as far as we can see, the limiting factor is the flux. The more photons that you throw at the sample, the more likely it is to degrade.
Right. I think there are some more hands up, actually, but we've hit 11:50, and I think that we need to start on the next talk, because I cannot stop him. Anyway. I need to explain a little bit of